And hopefully you can see me here on functions and graphs. Functions and graphs is a lovely topic because it covers a lot of the course. It ties an awful lot of things together. And when they changed the syllabus for the Leaving Certificate in Project Maths in 2015, as it was called then, they eliminated your opportunity for choice. You have to do the full paper, all questions. You can't leave anything out. You used to be able to. You could pick and choose topics that you didn't want to cover. Now everything is up for grabs. But it means that they connect everything together. So a functions and graph question can link to various things as well. So what I thought I'd do is I'd start today by bringing a lot of your course together up from the bowels of your knowledge there, so you know, tying all the algebras together, the calculus together, and all of that in a link through functions and graphs. So that's what I'm going to do. So bear with us. In your notes, you should have them there. There are notes that just have this rectangular piece there called functions and graphs with no maths on it. That indicates the start of a video session if you were to look at maths.griffith.ie. So if you're just interested in this topic, then it's just functions and graphs. So this session now for the next hour or so will be split into several mini topics. So you can just go back over exactly the bit that you feel you want to look at again, because you'll know most of it. Okay, so functions and graphs. This is a graph you've seen a million times. They were there in the junior certificate. They're nice. It's a quadratic graph. It's like swings nicely. It curves nicely. It has one minimum point, so it goes down and comes back up. And it's like a vase or a vase. Imagine you've got, say, maybe, you know, something, a bowl, and you might have a little marble, and you roll the marble down and it would end up at the bottom. Or you could imagine it maybe as sort of this bit above ground and this bit below ground, this bit may be filled with water or something like that. So that's what this graph is. It's given by the term y is equal to x squared minus 2x minus 8, this particular one, right? And this particular one bends down, whereas other ones would bend up. So this is bends down like that. We always talk about y and x because really all we have is paper, and paper is two-dimensional. So we've got an x-axis and a y-axis. We've got a horizontal, west-east, and a north-south or south-north. Okay, so we've got two directions. We've got the horizontal and the vertical. And we generally call that y and x. So y is a function of x. So for a given value of x, 3, for example, it has a particular value here. Now, if you were to describe this graph to somebody who was blind and say, what is it? Well, it's sort of, it's smooth, it sort of comes down and then goes back up. And they say, are there interesting points about it? Well, that's what we're going to do later. But for the moment, it's the graph of y equals x squared minus 2x minus 8. You'll also see it called f of x, or the function of x, is x squared minus 2x minus 8. That's the same question. It's just said it's a function of x, because y is a function of x. So it's really y equals. So sometimes the question will say fx, and sometimes it'll say y, but it's the same question. So really we're saying, what's interesting about this graph? Well, these points are interesting, because this is where the graph hits the horizontal. Let's imagine that this was above ground and this was below ground. Let's imagine that these were mountains and this was a lake and the water was filled here, and this were quite steep mountains now, maybe Italy or somewhere like that. You know, but basically you've got this sort of, you know, nice little lake there. So this is the level ground, and that's the level of the water, and that's above the mountain, and that's below in the lake. So there are 2 points of intersection. We call those intersections with the x-axis, because that's the x-axis. But actually, we call them also intersection with the y equals 0 line. So the x-axis is also y equals 0. So even though we don't often see it, it's almost invisible. Like when we see a piece of paper with graph paper like that, we almost think we're ready to start something, but we forget there's actually a line already there called the x and the y, and that this is the y equals 0 line, and that's the x equal to 0 line or function. So basically, this point here, this magic point 4 naught, is on 2 things. It's all on the vase, or the whatever this arrangement, but it's also on the horizontal. So it satisfies not only the blue one, but also the y equals 0. And the same for this. So it's intersecting two things. So they're interesting points. Another interesting point is this one here. This is where we look at the vertical and say the intersecting point here is, well, it's not west or it's not east. It's exactly just bang in the middle, like say Greenwich Mean Time or something like that, or a particular 0, 0 point here. So that's our intersection with our y-axis. Or again, it's actually our intersection where x is 0. So this is 0, 0, 0, minus 1, 0, minus 2, 0. The first number, the xy bit, is always 0 along here. So it's 0 minus 8. And this is probably the most interesting point on the whole graph, really. This is the point where the marble, if it was a vase and there was no water in it, would roll up and down, or maybe it would just roll until it was at the bottom. So that's where it would come to rest. It's the only place where it would come to rest. It's the minimum point. So that's what that point is. Or another way of looking at it is it's the point where the slope of the particular graph, the slope at that point, if we were to look at it here, the slope m dy dx or f dash x, whatever way you call it, when you're here, you're moving up the hill or up the vase. Here, you're moving down as you move across. But at this particular point, you're neither going up or down. You're exactly dy dx, or the slope is 0. And that's the only point the marble would stop. So if we look at the graph again from the very start, there's a lot actually going on in that simple, quadratic, expression there. Y is fx is this, so they're equivalent, where y is a function of x. Here you've got intersections with the x-axis, or y equals 0, here and here. Here you've got intersection with the y-axis where x is 0. And here you've got the one point where the minimum point is, where the slope m from the line, dy dx from calculus, or f dash x from another expression, or another way to write calculus, are all 0. So it's pretty inclusive, and it ties that together. So that's that topic. So now we move on to the next one. Basically, this is a new topic, mini topic with a little box on it. Let's explain what's going on here. When we put these notes together, we looked at every single topic on the Leaving Certificate syllabus that they're allowed to ask. We didn't look at the maths books, though we did, but we looked specifically at the Department of Education syllabus guidelines that all the maths books use, where it says students must be able to plot a graph, they must be able to intersect a line, they must be able to draw a line, find the slope. All of those things called learning outcomes that you're required to know, we took each of them in turn. So let's look at plotting points. So what we're saying now is, can you plot points on a graph? Any graph, if given the graph. So this small section here, which you will be well able to do, is just a reminder of that is on the syllabus. So we go through it just for completeness. Drawing graphs given an equation. So this is your standard Leaving Cert questions. Everything we're doing are examples of questions that have come up and can come up, covering the lot. So plot the function fx. You know that's y equals x squared minus 2x minus 8 for values of x between minus 2 and 4. In other words, find the value when f of minus 2, when x is minus 1, etc. So what we do here is we look at it and we say, okay, x squared minus 2x minus 8, f of x. What is the answer when x is equal to 1, for example? So everywhere there is an x, we put in a 1. So where x, we put in a 1, when it's x squared is 1 squared. Minus 2 times 1 minus 8. So 1 squared is 1. 2 minus 1 is minus 2 minus 8. And 1 minus 2 minus 8 is minus 9. And that's what I got there. So when I did f of 1, I ended up with the minus 9. So in other words, what we're saying is when I chose x was 1, so when x was 1, y or f of x was minus 9. So my xy value turned out to be 1 minus 9. So that's a point on my graph. I could have done f of 0. So 0 squared minus 2 times 0 minus 8 is minus 8. So I would have got the point 0 minus 8. And I go through each of those in turn. So I'm sure you're comfortable with those. If you can do one, you can do the rest. And there's the points that I got. So now I go on the graph and I copy them down and say, there's my 1 minus 9, there's my 0 minus 8, and I start filling them in on the graph. And then with something that you can buy, I think, in Tesco for a couple of euro maybe, you can get one of these things called a bit of a flexi thing. It's a couple of quid, it's just a piece of, you don't have to have one, but sometimes it's nice when you're sort of trying to draw a graph and you say, okay, that's that bit done maybe. I might do this bit here. And then I just look at this bit and try to get this bit a bit right. Now, so you get the graph and you see that you've drawn the graph, and you won't lose marks for doing it, inaccurately or something like that. But ultimately you want to get your curve and your drawing like that. And that's the job. There are marks for that. Can you plot a graph with data? So I'm assuming that that topic is done, but it's always there if you wish to go back. Next subtopic, intersecting axes. How do you intersect an axis with a function? What happens there? So here we're saying, where does this graph here intersect the x-axis? Now, if it's drawn for you, and sometimes it is, you can say, oh, it's at 4 and it's at -2. But very often they might want you to solve that either algebraically or graphically, whatever. So they say, where does this graph actually intersect with the x-axis? Now remember, the x-axis is a line y equals 0. So y equals 0 is the x-axis. So they're saying y is 0 and y is this. So this magic point here, let's call this A, and this point B. The magic point A, not only is it on the curve, but it's also on the y equals 0 line. So that's what we want to solve. And the same for B. B is on the curve and on the y equals 0 line. So note, this is y equals fx is this. Not only is y equal to the curve, but it's also equal to 0. And because y is y, this part here, x squared minus 2x minus 8, must equal 0. So if you look at that and you say x squared minus 2x minus 8 is 0, you've seen that lots of times in your course, lots of times in the book. Probably not in the functions and graph question at all. Probably somewhere completely different. Maybe just the solution of quadratic equations or something. Nothing to do with factors. Nothing to do with sort of quadratics in the graphical sense. So I said, oh, that's that part of the course. So they now want you to solve that. So how do we solve that? Well, one way of doing it is to get the factors. So some people are good at this, and they say x, the factors of x squared are x and x. Some people say 8, well, that might be 8 and 1. I don't think so. 4 and 2, maybe, yes, or 4 and 2 would be good. A -4 and a +2 would make it great, because then I get a -2 overall, and they do that. And some people will spot that. The factors. They'll say x plus 2 times x minus 4 is 0. And if x plus 2 is 0, well then, using the method, we can take the minus across. X is -2. And if x minus 4 is 0, x must be 4. So effectively what we're saying there is that the roots are actually -2 and 4. And -2 and 4 look correct. So they look okay. So they're the answers, the roots and the intersection points. So the factors, the roots, so the factors are x plus 2 is 0. That's a factor. That's a root, just turning it around where x equals, that makes it a root. And then the intersection points are there. But not everybody will be able to spot that comfortably under stress, or it might be trickier than that one. So finding roots using the quadratic equation formula can be used. Now, we would have done this for the junior certificate. So here we've got the y equals ax squared plus bx plus c. Remember, this is in the tables. You don't have to learn it off by heart. So, but on this occasion, we're dealing with x squared minus 2x minus 8, not ax squared. So what I do now is I go into a total concentration zone, and I say, okay, ax squared is x squared, so a must be 1. So the coefficient of the x squared must be 1. B, the bx is minus 2. Okay, so I'll write that down. And the c is minus 8. So now I can come up for air in a way. I've written them down. I've transcribed them. Now, if I make a mistake, they'll follow the slip and it'll be fine. But it'll just be easier. You know, it's neater, obviously, if that doesn't happen. But that's fine. I've got the 3 numbers. I'm now going to use those 3 numbers in the formula. The answer says x equals minus b plus or minus b squared minus 4ac over 2a. That again, I concentrated and copied it directly from the maths tables. And now I say, okay, I have to change these using these. So minus b, what's a minus b? That's a minus b. B is minus 2, so minus must be plus 2. The plus or minus I copied. The b squared minus 2, that must be, that's minus 2 squared. Yeah, minus 4 times, 4 times a is 1, and c is minus 8. And on the bottom, 2 times a. So after that period of concentration again, I say, okay, now it's just maths. So the plus 2 is there, the plus or minus. Minus 2 squared will be 4. 4 by 1 by minus 8, well, 4 by 8 is 32. 32 and 4 is 36. And the square root of 36 is plus or minus 6. On the bottom, 2 times 1 is 2. So now I have 2 answers, 2 plus 6 over 2 and 2 minus 6 over 2. Let's take the top one. 2 plus 6 is 8, and 2 minus 6 is minus 4. 8 over 2 is 4, and minus 4 over 2 is minus 2. So again, I get exactly the same roots. X is 4 is a root. X minus 4 equals 0 must be a factor. X is 4 is a root. Minus 2 is a root. The intersection points must be 4 naught and minus 2 naught because we were told that y was 0. There we have it, the intersection points, and we have it. We know that the intersection points are A and B are 4 naught and minus 2 naught. So that's intersecting the x-axis. The next one is intersecting the y-axis. How do you find this point C here? Well, it's pretty much the same idea. Any intersection of anything, anywhere on your course, is 2 things coming together. So it not only must be on one thing, it must be on the other thing. And remember that in the case of the y-axis, x must be 0. So x equals 0 is not just an algebraic expression. That's actually a line, a function. It's here, it's the actual full vertical thing that everywhere along here, whether I go up to the very top or down to the very bottom, x is always 0, neither east nor west. Also, y is equal to x squared minus 2x minus 8. But I know the value of x, so I can plug in the 0 into it. So y is equal to that, x is equal to 0. So I can substitute everywhere there was an x with a 0. So f of naught is naught squared minus 2 times naught minus 8, which is really minus 8. xy is naught minus 8. And that's pretty well where it ends up. Naught minus 8 is the intersection point. And that's that. So the question is now, you say to yourself, can I plot points? Yeah. Can I find the intersection of the x and the y axis? Yep, fine. Let's do something else. This one here is a slight variation on that. It says functions and graphs, checking graph values. And basically it says, is this point here, 0,3, on the graph? Well, it certainly doesn't look like it is, that's for sure. think it's way off it, but maybe I drew the graph badly. So let's just see what the graph was. I think the graph was f of x, x squared minus 2x minus 8. And is the point 0.3 on it or not? Could I have drawn this incorrectly? Well, what you do is you say, let's check the point 0.3, is it on it? Well, let's try the value where x is 0. So when x is 0, we get 0 squared minus 2 times 0 minus 8, or we get the point 0 minus 8. Well, this is saying that when x is 0, the y value is minus 8, not 3. So 0.3 is not on the function. So when this graph was going down there nicely, look at it here. When this graph was here and smooth, when x was 0 here, I looked down. I could see that it was passing at minus 8, not above me at 3. So that's not on the graph. And that's all you'd be asked to do. Again, that's one of the questions that they can ask. Now, then they say, okay, where is the graph f of x greater than 0? Where is the actual graph above the actual horizontal? So we can see here that after the point 4, that the blue line comes out of the water or up the mountain or whatever we call it, that this is the bit that's positive. And similarly here, below minus 2, further back here, it's positive as well. Whereas in the middle, the blue is sort of underwater. So the question is, where is f of x, or where is y greater than 0? Well, certainly in this bit here, when x is greater than 4, and here, when x is less than minus 2. And you just write that out. So there you go, when x is greater than 4 or x is less than minus 2. Now you can write that as x is less than minus 2 and x is greater than 4 as two things. But sometimes it's nice to write it in two different ways. So let's imagine that somebody gave you a question and they gave an expression that says x is less than minus 2. As I move from x to minus 2 and look across, I sort of hit the pointy bit first, and then it opens up. So going from x to minus 2, I hit the pointy bit first, moving from x to 2. So if I were to put the x here and the minus 2 here, as I move from x to the minus 2, I should hit the pointy bit first. Or equally, if I go from minus 2 to x, I should get the mouth of it open first. So minus 2, open mouth into x. So that's the same as that. They're equal. So instead of x less than minus 2, I get minus 2 less than x. X greater than 4. And then I can just write it as one piece. I don't have to do that, but very often the question can be written like that, where minus 2 greater than x greater than 4. And really all they're saying is, just be careful. This is true, minus 2 is greater than x, and also this is true, x is greater than 4. So there's two parts, and you can flip that again to say the other way around if you want. You can put the x here, and because it's minus 2, you do it this way, minus 2. Okay, so that's how you do it. So I'm just saying that they might write it like that. You don't necessarily have to write it like that. So that's that bit. Now, what else do they have in the course for you? Well, they have this thing called intersecting lines. And they say, well, how do we do that? Well, I thought we did that before. Well, we did, but the lines were sort of easy. They were the x-axis or the y-axis, or the y equal to 0 and the x equal to 0. So how does it work now for functions and graphs? Okay. So lines intersecting the graph twice. What values of k does the function y equal to fx equals k intersect the function this twice? Now, they'll have given you a graph of this, but you say, it seems so complicated. Observation, fx equals k, y equals k is like y equals 2, y equals 7, y equals minus 17.6. That's a k value, okay? There's no x's here, so that must be a straight line. And if the y value is a certain height, it must be at a certain line, certain vertical height. So for example, y equals 0 is the x-axis. So let's look at this question. What it's really saying is there's your graph, y is x squared minus 2x minus 8. And this is the line y equals 4. So when y is equal to 4, you can see that you'd cut the vase then twice. If you were to come down to y equal to 1, you'd cut the vase twice again, or down to 0, you could see that you'd cut the vase, because you might remember we had actually intersection points at minus 2 naught and 4 naught. And we could keep going down further in the water until eventually we'd reach this point where we'd be at the bottom. And after that, we wouldn't be cutting it at all. We'd be back on solid ground again. We'd be below the lake. So really the question is, what is the lowest level line that we can see that actually only hits the graph once? And this is a visual question. So you just look at your graph that you're given and you say, that's not 8, I reckon it's about 9. I'd say it's about minus 9. When y equals minus 9, I think you're only hitting it once. Certainly by minus 12, you're way underneath it. At 6, you're still hitting it. Minus 6, you're still hitting it. So by I, it's minus 9. So all horizontal lines above the line intersect the original function twice. So basically what they're saying is that at any point above minus 9, no matter how far I go infinitely, there'll always be 2 bits of that function that I'll be hitting. So when k is greater than minus 9, when k is equal to 9, obviously it just hits it, well, once. Well, you might have 2 identical roots, but only in one spot. Now, that brings us naturally onto the other part of that question, and then say functions in graphs, maxima and minima. How do you find out what that minimum or the maximum is? So a turning point, or a place where you go from going down to going up, or up to coming down, is where the slope of the graph is horizontal. And this happens when f dash x, the first derivative, and k dir hiach, for those that den was Gaeilge, differall, no, k dir hiach, f dash x, cut to dy dx. So when f dash x is equal to dy dx, when that's equal to 0, when the slope is 0, we'll actually see later that that's m equal to 0 on the whole line thing. But for the moment, let's just stick with dy dx and f dash x equal to 0. When is the slope equal to 0? Well, in order to do that, we're going to calculate the derivative of the original function. So y equals x squared minus 2x minus 8. Now, we'll do a topic on calculus later. But for the moment, we'll just say, let's see if we can calculate this from what we know. We have a rule in calculus that said the dy dx, and k dir hiach, if it's x squared, you take down the 2. And you make it 2x, and you reduce it by 1, so 2x to the 1. The minus 2 stays. If it's dy dx of x is just 1, and dy dx of a constant minus 8 is nothing. So it's minus 8, it doesn't depend on, x or y, so it's 0. So dy dx here turns out to be 2x minus 2. That's the slope of the graph or the vase at any given time, okay? Now, we're asked, when is the derivative equal to 0? We're not interested in general, but when is that equal to 0? So when is 2x minus 2 equal to 0? Well, 2x minus 2 is 0. I don't like the 2 on the left-hand side. So 2x, I'll say plus 2 equals 2. I don't like 2, it's a multiplier. X equals 1. So it looks like the turning point for this graph is when x equals 1. Now, that just tells me when it turns, what x value it turns at. But I need now to know the point it turns at, not the slope, but the point on the graph where it's sloped. So then I've got to go back to the original graph. Now, the original graph, you remember, was f of x was x squared minus 2x minus 8. And now I'm going to plug in f of 1 for that, because I know 1, the value x, is where it's interesting. So 1 squared minus 2 times 1 minus 8 is a y value of minus 9. So the xy value is turning out to be 1 minus 9. So the local minimum point, I know it's a minimum point because I've drawn the graph. If they wanted me to prove it was a minimum point, I could do other things as well. But at the moment, I found the local minimum at 1 minus 9. So let's just look at that graph and see exactly what's happened in all the calculus. We have here the graph y is equal to, or if we want, fx equals, right? We've calculated dy dx. Is that okay? We've calculated dy dx here, or f dash x, the same thing, k dir here, no dy dx, diff for all, is equal to 0. We know that the slope at this point is 0. That's the only point it happens. Now, we got the slope dy dx is equal to 2x minus 2. That tells me that the slope isn't always 0. Like when x is 3, for example, 2 times 3 minus 2 is 4. So when x is 3, the slope is 4. It's going up. When it's 4, it's higher. When it's 2, it's not as high. Here it's 0. When the slope is minus, when x is minus 2, 2 times minus 2 is what? Minus 4. By plus, that's another minus 6. It's really coming down here. So the slope is also changing. Very, very steep down, not as bad, not as bad. Easy enough climb, getting to the top, really impossible. So you can see that whole idea there in terms of the slope. But the only point of real interest to us is this one here, where the slope is actually 0. That's why we want dy dx. Not only dy dx, but we want dy dx to equal to 0. And that's where we have that. So that's 2x minus 2, and that happened when x was 1. We then knew it was underneath this point, when x was 1, that the slope was 0. But the way we found the point was by saying, well, it's not just good enough knowing that x is 1, but if I plug 1 into this, I'll get the y value. So 1 squared minus 2 times 1 minus 8, 1 minus 9. And that's how I solved it. So that's that. So that's how we get the minimum. That's how we've got lots of the graphs. But there are other interesting points besides the minimum points, and that's other slopes. Because dy dx works for all the values of the function. So here, if we look at all the syllabus, they say students are required to be able to see which is the best and whatever. This page is taking a little bit of difficulty with the camera, so apologies. It's just the lines there are very close together. Basically what they're saying is, when is the slope greater than 0? So I'll try and do this and maybe it'll calm it down a bit. Basically along here, the slope is negative. Negative, 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 negative. And once I start coming up here, you can see that the slope is going uphill. So after this point, after x equals 1, you can see that the slope dy dx is greater than 0 when x is greater than 1. Or you could say f dash x. Make sure the dash is visible there. Okay, so that's how we do that. F dash x is greater when x is greater than 1. Now, the next question then is, find the general expression of the slope of the function. Well, we did that before. Find dy dx, or, feig k dir here on Sloan Carnick. So you get dy dx is 2x minus 2 there. That's the formula always. When is the derivative equal to 4? What they're asking there is, when is the slope of this thing equal to 4? When is it sort of going up at such a height again that it's 4? 4 would mean that for every step out, one step out, I go 4 up. So that's quite a big ladder that I'm climbing. It's quite a steep hill. So when is dy dx equal? Well, it's the same as doing dy dx equal to 0. I just say, when is dy dx equal to 4? So when is 2x minus 2 equal to 4? When 2x is equal to 4 plus 2. When 2x is 6. When x is 3. Okay, So this is telling me when the x value is 3, the slope is 4. That doesn't tell me the point now. It just tells me the x value. To get the point, I have to put 3 into the equation again of x squared minus 2x minus 8. And I find that when x is 3, y is minus 5. So the point 3 minus 5 has a slope of 4. So if I look at the graph here, x squared minus 2x minus 8. At the point 3, if I go down, I'm really going uphill now. That's really quite steep. And actually, for every step out I go, I'm going up 4 units for every step out. The scales aren't exactly, they're not equal there. So, but it is 1 to 4. So the slope here is 1, it's 4 over 1. So the delta y, the change in y over the delta x as I go across there is dy dx is 4. Or you might say y2 minus y1 over x2 minus x1, or y0 minus y for the line there. You can get it that way for m as well. But again, really what we're saying is that the slope here at 3 minus 5 is 4. So that's f dash x. And there's a graph of it. So at that point, we're going up. For every step out, we're going 4. Whereas here, it was horizontal. The slope m is 4 over 1. So for example, if this was sort of, let's say we made that little bit bigger, and we showed it this way on paper, and we just take that little section there, that triangle there, and let's say it was, let's say it's 1 to 4. This could be x1, y1. This could be x2, y2. So that would be y2 minus y1 over x2 minus x1 is m. That's the line connection there. It's that height. So you'd see that the difference here, this delta change here is 4 over 1. It's 4 over 1. So that's the slope. M, the slope of the line, is actually f dash x, is dy dx, is 4. And if I really wanted to connect your heads all together with the other parts of the course and show you what's possible, that's the angle theta. That's a right angle triangle. That's the opposite. Opposite over adjacent. It's tan of theta. So many parts of the course are linked together. The slope from the line, the f dash x or the dy dx from the calculus, the 4 is the answer, and the trigonometry, all coming together in the point of that slope there. So functions and graphs, we're nearly there. We've now found where the slope is 4. We found the point where it's 4, and we're now going to do the tangent to the curve. This is really now jumping into the line question and how you would draw a tangent. Find the tangent to the function fx is equal to x squared minus 2x minus 8 at the point 3 minus 5. So we're going to go to the point 3 minus 5. The function is the function we had, and we're going to see if we can actually draw that, if we can draw that tangent. It would be nice if we could find out what that tangent was. What is the function? What is the equation of this tangent? How do we get that? So the point is 3 minus 5. We know that because that's the point of interest. We've been told that we're interested in here. We've been told it's 3 cross and minus 5 down, and we know the slope is 4. So the slope m is given by 2x minus 2, always. That's dy dx, always. But the point is 3. The slope at point 3 is given by 4. Because that's when the slope was 4. That's the only point, indeed, on the whole graph where for every step out, I'm going 4 up. Here it's higher. Here I'm going down. Here it's 0. But that's the only point where the slope is 4. But we jump to another part of the course now, and we say, but we don't have to work this out because there's a formula in the line section in the tables that says y minus y1 is m into x minus x1. Really what it's saying is, if you have a point, x1, y1, that you know is on a line, in this case, we know it's 3 minus 5. And if you also have a slope, you can draw a line. You can draw the equation. So very simply, if I've got any graph paper here, and I know that's a point of interest, and I know this is the particular slope, the slope is 1 in 4. Well, if I know m is 4, and I know x1, y1, there's no other way. I mean, if the slope was different, it'd be a different line. So once I know the slope, it's here. I know the slope. And if I know the point, well, it must be the point that has that slope through it. So there's only one line in it. So effectively what I have now is I've got the tangent is given by this equation. So I carefully have written down here, before I turn that page, I say, oh yeah, x1 is 3, y1 is minus 5, and the m is 4. The slope, there's my points. So my x1, y1 was 3 minus 5. Okay, so now very concentrated, I'm in the zone, I just transcribe Ashgrave. I say y minus y1 is m into x minus x1. I get marks for that, for taking that out of the tables and knowing it's the right one to use, or that I can use it. So y plus, oh yeah, y1, that's minus 5. So y plus 5 is m is 4. X, yeah, x minus x1, that's minus 3. So that's the equation now in that sense. Okay, there's the equation. I can come up for air and I can say I get it, but let's do some just arithmetic or algebra, moving it around a bit. So I'm going to multiply in anyway first. So I'm going to get y plus 5 is 4 times x minus 12. Maybe I'd like the x on the other side. So I'm going to say equals y plus 5. So I'm just going to turn it around. So that's all that's going on there. I think I'll move the 12 over to that side. So I get 4x is y plus 17. And I'm going to take the y back. 4x minus y equals 17. So very often you see lines written like that. That's an equation. You would have seen that in different simultaneous equations, for example. So that's one way of writing it. Or another way is to get this. So let me just take that step and do it slowly. I can write this any way I like. In so many ways I can choose what I want on the left-hand side. But 4x minus y equals 17. So let's say I just wanted the y on its own. That was my point of interest. Well, maybe I'll move it to the right-hand side. So I get 4x equals 17 plus y. That would solve that problem. So I'd add a plus y here and a plus y here, and that cancel. Okay. Then I get the 17 on the other side. I think to get rid of that 17, I don't like it. So I get y is equal to 4x minus 17. But I'd much prefer if it started with the y. So y is equal to 4x minus 17. And that's what that is there. Okay, that's another way of writing the line. So I can write it any way I like. The good thing about writing it like that, though, is if y is equal to 4x minus 17, dy dx, or f dash x, is just 4, because the 17 would cancel and the 4x would become 4. And that is the slope we had anyway. So it is reassuring that it's right. So there's the tangent. There's the line. That's the equation of the tangent on Tylee ag an buinte 3 minus the coequation on Tylee, Cortamod on Tylee, y Corme car x minus shock there. So the equation of the tangent at that point is y is 4x minus 17. And that's the tangent at 3 minus 5. And that's that topic. Okay, so we've done lots. We've moved now to done lines. We've done lines that were not just the XY graph, but we've done slopes as well of tangents. So now we're going to look at intersecting functions. We were doing it all along, really, because the x-axis and the y-axis are two functions and they come together at naught, naught. But these are a bit more general than just the straight lines. So the intersection of two functions. Find where the function f of x equals this, our original one, intersects with the function this. So now we've got a new function, g of x is minus x minus 2. Now, don't be put off. F of x is just really y, because we only have paper. We only have 2 dimensions. So g of x can't be something else. It's just a different version of y. That might be y1, and this might be a y2. But it's still going to be drawn on graph paper. It's still going to have the x and the y axis. So we're still going to draw it in the same way. It's just we're going to use these numbers instead of those numbers. That's all. So find where the 2 graphs are equal. Now we're going to do this first without doing graphs. We'll do it later with the graphs, with the visuals. So when are they equal? Well, fx is equal to gx when this equals this. When x squared minus 2x minus 8 is equal to minus x minus 2. And really, that's just an equation. So we can simplify it across. We can say, I don't like the x on this side. I'm going to take it over, make it a plus. I don't like the minus 2. I'm going to take it over and make it a plus. So I end up with x squared minus 2x minus 8 plus 2, or x squared minus x minus 6 equals nothing. That's f of x, or the new one we have. That is no different in terms of difficulty or ease to the one we've been doing all day. This one here, the x squared minus 2x minus 8. It's just got different numbers in it. So the same question applies. What are the roots, or when is that equal to 0? So when is x squared minus x minus 6 equal to 0? That's algebra. It may not have to be drawn as a graph. It's a quadratic equation. We can solve it. So people might be good at the factors, and they might say it's x and x. 6 is probably minus 3 and plus 2, and they'll get the factors that way. And with minus 3 and plus 2, if x is minus 3 is a factor, x equals 3 would be a root. If x plus 2 is 0 is a factor, x equals minus 2 would be a root. So the roots seem to be at minus 2 and at plus 3. And that's one way of doing it. But again, let's say you didn't spot it, or you don't like solving it with the factors or whatever. You could use the ax squared plus bx plus c method again. Go through exactly the same thing, use the formula, plug in that, well, in this case, a is 1, b is minus 1, c is minus 6. Plug in all the numbers, go around the cycle again, and you'll find you'll get x is 3 or x is minus 2. Exactly as before, if you had done it with the roots, or we did earlier. Now we want to calculate the points, not just the value of x at that point, but the point itself. So what is the y value or the gx value at that point? Well, let's look at it. Well, the gx is minus x minus 2. So when x is 3, which was one of the roots, the point seems to be minus 5. So 3 minus 5 seems to be one of the points of intersection. When x is minus 2, it looks like it's minus 2, nothing. So there are the values, at least on the g function, where we reckon the points of intersection are. 3 minus 5 and minus 2 not. We can check that by putting them into the f function, and say, well, let's plug in the same numbers when x was 3 and x was minus 2. And again, we get 3 minus 5, this one here, and minus 2 not. So exactly the same points. So we've done the calculations right. If we had drawn it, we would find that this is the f function, the original blue vase that we had, and this was the g function. Y is gx, remember? Y is fx here, so it's the same y, but in this case, gx is minus x minus 2. So if we put in, say, when x is nothing, this must be minus 2. When x is 5, here, 5 minus 2, minus 5 will be minus 5, minus 2 will be minus 7. So when x is minus 2, minus minus is plus, we'd end up here, etc., all the way along. And that's our g value. So we can plot the graph of that, only it happened to be in a straight line. We could have drawn loads of points there as well, but it would have been just a straight line. And that's graphing the intersection. Now, they then ask, when is f of x greater than g of x? Well, when is the blue graph above the red graph? And again, by eye, we can say, well, it's certainly above it here, much higher, and certainly here. But in this bit here, it goes below the red. So for this section here, the red line is above the blue line. But the question is, says, when is the blue above the red? So when is fx, when is blue greater than x? Well, it looks like it's when here, when x is greater than 3, and here, when x is less than minus 2. So x, again, less than minus 2, x greater than 3. And you can go through the same process as we did before. You can have x less than minus 2. And you can rewrite that if you want, x minus 2. And going from x to minus 2, you got the pointy bit first. So you get the, and 2 minus 2, you get the open mouth bit first. So there's the 2 and the other, and you can join them together as one equation. So that's the function there for that. Again, you could draw this, and you could say, this is getting a little bit, the camera here is going a little bit crazy. But again, you can see it in your notes, it'll print out a bit better. That basically, in this section here, f of x is less than g of x. But on both the other sides, it's higher. Okay? And that's the graph. It's just that the lines are so close together, the camera's having a little difficulty there. So we're nearly there. We're coming towards the end. And I'll just show you a few other graphs that are not different, really. There's nothing new about them. They just look nicer. It's the same techniques, but don't be put off by them. These are called inverse functions. Inverse functions are graphs that sort of have a 1 over x in them. So plot the function fx is equal to 1 over x plus 2. So fx, or y, equals 1 over x plus 2. Between the values minus 6 and 2. This is no different to any other question. It just has values of x's. Can you plot points? You can. When x is 0, it's 1 over 0 plus 2, which is a half. When x is 1, it's 1 over 1 plus 2. So you just plug in the values as you did before. What's f of 1? What's f of 2? What's f of 3? And you plug in the numbers for plotting graphs exactly as you did for plotting points. Now it says avoid the point minus 2. Because 1 over minus 2 plus 2 plus 2 will be nothing, and 1 over nothing is not defined. But you could get close to it. You could maybe use minus 2.1 or 2.5, and then minus 1.5. So here we have the numbers. I put in minus 6, minus 5, and enter the values, just as you do for plotting points. And I've done them along all the way. I've used ones near minus 2, just at minus 1.5, just for interest. And the graph, when I plotted it, turns out to be nice. Just turned out to be that graph. It's a graph that sort of has 2 parts to it. You don't have to do anything with it. It just draws nicely, and that's what it is. And this point here is just called an asymptote or something like that, because it never actually makes it. It just nearly gets it and comes in back from infinity at the other end or something like that. Nothing to know, just a nice graph. Plug the numbers in and draw it. We'll now move on to cubic graphs. Again, very little that's different here in cubic graphs, only just a bigger expression. Here's a nice graph. It's fx equals, or y equals. Again, we've got 2-dimensional paper. We've got a y-axis and an x-axis, or a y equals 0 line and an x equals 0 line. And we plug in the numbers. When x is 0, we say 0, 0, 0, 10. So the point 0, 10 is there. And if we put in the value 2, I think 2 cubed is 8 minus whatever. We can work it all out, but it probably ends up there. Okay, let's assume it does. It's just f of 2. Well, 2 cubed minus 6 times 2 squared plus 3 times 2 plus 10. So that's 8 minus 24. Is that 6? I think that's minus 16 plus 6 plus 10 is not. So that's right. We can imagine that we can draw all the points. This is an interesting graph by eye because there's a root here, there's a root here, and a root here. And we might be told that, or we may have to find them. Okay? There's a local maximum at the top here. It's local in that there may be, well, there won't be, there's a minimum here, but at this region point, you go up a hill. Now, it's not the highest because it's not the highest max because that goes up here, but it's local at that point. It's like a small hill or something. So the dy dx and k here differ all. F dash x, annoyed. The first derivative is equal to 0 there. Again, uaswinta, right? That's the local max. And the easwinta down here, the local minimum, dy dx is f dash x equal to 0. So that's the graph. Now, this point here is a point of inflection. It's if you're driving a car and you're sort of coming into one bend, I don't know if you can see my hands, and then suddenly you turn into the other one. You're coming around one turn and then into the other. It's almost like you're just getting over this hill and then you have to sort of maybe come around to your right and then you just turn into your left or something like that. That's that sweet point, I suppose, where you're just out of one and just about getting into the other. And that's where the do y dx carna, or the second derivative, or f double dash x, is 0. And that's that point of inflection there. So there's the graph of x cubed minus 6x squared plus 3x plus 10. And actually, you can get the dy dx, and you'll find that dy dx of x cubed is 3x squared. dy dx of 6x squared is, I think, 12x, but it's a minus. dy dx of 3x will be 3. So that is actually a graph of dy dx. I've just decided to draw that. And you can see that at this particular point here, the dy dx is just bottoming out under the point of inflection. Whereas here, the dy dx graph itself is 0 because the main graph has hit a minimum. The dy dx here is 0 and the main one has hit a max. So it's just a nice way of showing the two graphs on top of each other in a way. So there's the cubic graph, and there's the derivative, the f dash x of it. And you can see that that's the red one, and that's the green one there. I put in the next derivative, which is the 2y dx squared, and Dorodir here, the second differential. And that gives us this line here. And you can see that that's a straight line. It's just 6x minus 12. And again, that's 0 here when the second derivative is 0. And then I did the last one just for the fun, the third derivative, and that's just a straight line. So it just happens to be all 4 if you were asked to draw it. You just plug it in on the same graph and it's done. Now, so that's the end of those, the cubics. Now we look at the logarithmics and the exponentials. These are nice graphs. These are the ones with the log and the e to the x, or the natural log. Here we've got a graph of y is equal to fx is log x. Log x looks tricky. It's not one you do very often, but it's no different to anything else. This is y equals log of x, or f of x equals f of x is log of x. It's no different to the one really where we said x squared minus 2x minus 8. If we want f of 1, we just, everywhere there's an x, we put in 1. So f of 1 is log 1. F of 2 is log 2. F of 3, log 3. It's just a y and a function of x here, and you just plug in numbers. So if I want to do that, I can plug in the value when x is 1, 2, 3, 4, and I can draw the graph. The y will always be the vertical, the x will always be the horizontal, and this is the graph of y equals log of x. I just plugged in numbers. If I want to do the derivative of that, what is the derivative of log x? Well, I can look that up in the log tables because there's a mapping for that. And it's on the table there. And I think if y is equal to log x, dy dx, or f dash x in the tables, I think they say is 1 over x. And again, when x is 1, I plug in a value. When x is 2, I plug in a value. And that's the graph of that. So again, I can draw that graph as well. If somebody said draw the graph of y is equal to e to the x, I say, what's the value when x, or f of x is equal to e to the x? What's f of 1? E to the 1. What's f of 2? E to the 2. E to the 3. I draw the graph. And e, of course, is 2.71828 or whatever. And it's on your calculator anyway. So that's the answer to that. So that's how you solve that. So there's the graph. And the only good thing about, well, it's what's special about fx is e to the x, is if you differentiate it, you get the same graph, the same graph, the same graph. So this is not only e to the x, but the derivative of it, when k dir here, con dara dir here, f dash x, f double dash x, forever. It's the one graph that when you differentiate it, it stays the same. And thank you so much. You've been with me for so long, and it's been so long to do all this, but I'm virtually finished, and this will take maybe the 2 minutes. The next session won't be as crammed packed, I promise. So thank you for that. Finally, there's this final type of functions and graphs where they'll just show you something that's quite different to anything you've seen before, and you're to use the graph to read from the graph. You won't have any calculations or big, differentials to do. So here's a graph that's very sort of jagged and quite rough. And instead of saying y equals f of x, they have this f colon x with an arrow, which is very nice. But really, from your point of view, it's just another two-dimensional yx graph. And you can see here that it's sort of repeating itself every so often. Now, you might have watched, I'm sure you do, everybody watches the medical drama TVs and stuff, and there's always somebody there being looked after, and then it gets really sad. And you're watching and you don't know whether it'll come, and they'll try this and they'll try that, and then just before the end it happens. Or sometimes actually it doesn't happen, and that's worse again. But basically, we've all seen that, the heart rhythm or whatever. So what we try to do is, and what people use these for, is they say, that's the repeating pattern. And in the repeating pattern, they say, how many seconds is that? Or how many units is that? And also, what is the max height? So how big was that peak? So it might be your heart rate when you're monitoring your Fitbit or whatever you do to keep all those various devices. You can see this pattern of sort of a particular biorhythm or something like that. So the question here is, what are they? So identify the period and the range shown in the graph. So here you've got the graph. It'll be given to you. You won't have to draw it. So what's the period? Well, in this case, I could start by picking two high points, one after the other, and say, what's the gap between those 2 points there? And on the graph I have, and hopefully in your notes, 6 to 16 is a gap of 10 away. I could have gone to this one here and that high point, and I still would have got 10. Or I could have chosen the 2 points at the bottom, or the points were across the x-axis and they were going up, and I would have got 10. The range is the difference between the lowest value, and on the graph here, that's at -1, and the highest value will be +3. So that could be a blood pressure reading or a fitness level or whatever. So the question is now asked, find F4, find the value at time number 4 on the graph. And what you do there is you go in at 4, and you go up and you say the point is 4, 2. You read it from the graph. And the only bit that's tricky is it says, find the value at f of 84. So you look across here and say, that's 4, that's 14. But 84 is miles out there. I can't do that. I don't have f of 84. But what you can see is the pattern is repeating. So every 10 units, this thing is repeating. So 4 is the same as 14. So every 10 you can cut away. So f of 84, you could take 10 from it and get f of 74 instead. Still be off the graph. But you go further, take loads of 10s off it, maybe say 10 of 24. Would that be okay? No, not enough. We'll try f of, effectively you can say how many 10s are there in the, so you can say, I reckon it's 10 per unit, be 8 units. If I took 8 10s, I'd go from 84 down to 4. So f of 84 is equal to f of 4. So 4 is the same as that. F of 84 is 2. And that's the very end. So thank you. I'm sure you're exhausted. And thank you for your attention. Hopefully some of those things were straightforward for you. Most will have been. But hopefully there was somewhere along the way a gap that you filled in or a hole you filled. So thank you. I'll be back at 11:30 and the next session won't be as cram-packed. So Gurmil Magav, Slán Tamil, Slán. And I'm back. So Fáilte Róibh Harash, Tomás and Shaw. And I'm going to go through the questions that Sinead kindly sent me on a WhatsApp line there that we set up. So thank you. I'll take them as I see them. And we just take a minute or two before we start the other. So Luke says there's a question about logs. If there is no base, if they don't tell you that it's base 10, can you assume it's base 10? And the answer is yes, really. I mean, if it says ln, it's natural log. If they call it log, you can pretty well assume that it's log base 10 they're talking about. Now, if it turned out to be a different log, let's say it was log base 4, which is really quite strange, or log base A, we'd have to find a way to undo that. We know that the log of 10, the way to get rid of that is a 10 to the power, so that will solve it. We know that e to the log will get rid of it. 10 to the power of that would get rid of it. So 4 to the power or a to the power would get rid of the others as well. But back to Luke's question, if they don't say, and it's log written, it's assumed to be 10, base 10, your standard log in your calculator. Alana asked if calculus could be used in the coordinate geometry question to solve a problem, or would be better off sticking to the formulae there. The choice is yours, Alana, entirely. Whatever works, you can solve a problem lots of ways, but you're probably familiar with the coordinate geometry and the line that way and do that, that's fine. But it's just when you're stuck with the question, any solution that you find would work for you, use it, because it's picking up marks and it's what this course was about, being able to join the various bits of the course together, and a real success for the syllabus. Okay, does the maths revision course we're doing today cover everything? Well, unfortunately not, but it covers a few topics. What we're doing on the higher level maths today is that we're deliberately covering topics fully, comprehensively in the topic areas we're doing. So we're picking 4 today. We're picking we're going into calculus now. We've done the functions and graphs, and we'll do the other two, the complex numbers and the probability. There are other topics on the course, obviously, lines, circles, and all those. And there's loads of resources on maths.griffith.ie, both as Gaeilge and as Béarla. So you'll see other sessions there, not entirely everything, but we're working towards it, and we'll do that. So, you know, we'll keep on tipping away at it. But we took the ones today that we felt would tie a lot of the course together and fill in some of the holes. Most importantly, what I want to achieve out of today, if just one thing, is to, I suppose, convince you yourselves that the holes you have, if you filled in some of those, well, sure, you can fill in the others. There's nothing more difficult about the stuff you don't know yet than the stuff you've already picked up. So, you know, there's really just a question of where's that gap, and hopefully finding a tool to find the particular solution or the stone you're looking for there. Ananya talks about the inverse of a function. How do you calculate it? I don't think you'll be asked to calculate the inverse of a function, like sine inverse is an inverse. Maybe, you know, 1 over x is an inverse. But generally they'll give you a graph and they'll say find. Or if there's a graph and they say find the inverse, they might say find 1 over y, and you just turn it upside down. So there's no question about without some more information that they'll give you on it. this question has come up a bit about the maximum point, and I'll just talk about that. This is example here. Here's the original graph, and this was our, I think, our minimum point here, and we said dy dx, I think, turned out to be 0 here at the point 1, 9. dy dx was 2x minus 2. So the question really was, how do you know that that's a minimum point if you haven't drawn the graph? Well, there's two ways of doing it. One is to say, well, dy dx at the point 1 is 0. So maybe go back a little bit further and say, what was it at 0? So dy dx at 0 would have been minus 2, and dy dx at 2 was plus 2. So it was going from minus to plus. So the slope was going from minus to plus. So if the dy dx was going from minus to plus, that'll be a minimum. So you can do that by finding the values. And in fact, if you found the value, you just need to go back one of them and say it was higher there, so it must be a minimum. Now, let's imagine that you did the graph and it was slightly different. And let's say the graph was the same graph as that. Oh, sorry, the other method of doing it, sorry, is explained. The second, shorter way of doing it is at the same point, find the second derivative at that point. d2y dx squared at that point would be 2. So the second derivative at this point is positive. And if dy dx is 0 and the second derivative is positive, it is a minimum. So I'm going to take that graph, and instead of drawing it like that, the way it was, something like that, I'm going to draw the opposite, and I'm going to imagine the graph was like that. So I'm going to put a minus in front of everything. So let's imagine that the green graph is minus equal to minus x squared minus 2x minus 8. Now this would be the mirror image of the graph, and this would have a maximum up here rather than a minimum down there. How would you know it was a maximum? Well, you'd get dy dx. dy dx at this would be minus 2x minus 2. You'd make that equal to 0, and you'd say 2x on the other side. Say that again, get that right? Yeah, minus 2x, oh sorry, apologies, that was a plus 2x, because I have to make minus for everything. So it'll be y is equal to minus and be plus 8. So the graph I have now, the green graph, that's its equation. So the dy dx of that would be minus 2x plus 2. So that would mean 2x is 2, x is 1. So it would say that the maximum was when x was equal to 1, exactly as it was for the red graph, but just top now. How would you prove that that was a max? Well, if dy dx was equal to minus 2x plus 2, the second derivative, on Daradir here, dy dx carn will be minus 2. So if the second derivative is negative, at a dy dx equal to 0, it's a max. So max, we'll write that out, max dy dx equal to 0, d2y dx squared negative. And a min dy dx equal to 0 and d2y dx squared greater than 0. Okay, that's one way of doing it. Another way is to just get the dy dx slightly to the left or to the right. So obviously if it's going from up to down, it's a max, down to up, it's a min. So there's the rest of the questions. I think I've got them all there on that. Oh, there was one, and how do you find it's a local? So that's Louise's question. The second one as well, it was a common question. So just Louise, you've sent in two, so you might just resend in the first so that I can answer it fully. Okay.